All right. Good evening, everyone. My name is Sergey Vasilyev, and I'm a second-year astronomy graduate student at UC Berkeley. I research exploding stars and ripples in the fabric of space-time to measure the expansion of the universe with Professor Alex Filipenko. This is the story of an emerging era in astronomy. For centuries, we have studied our cosmos by capturing light in telescopes. Just several years ago, LIGO revolutionized the way we do astronomy with their detection of gravitational waves from a merging pair of black holes. This talk will give an overview of the amazing astrophysics that can be done by combining light and gravitational waves with an emphasis on one of the biggest problems in cosmology. And that problem is the Hubble tension problem. So how did we get to where we are today in astronomy? Well, before 1609, we only knew how to use our eyes to study the sky. It was not until the time of Galileo, until we had a tool to let us capture more light into our eyes from the planets, stars, and galaxies. And for 400 years after Galileo, we only were able to study visible light, which is the electromagnetic radiation that our eyes can see. In the late 19th and early 20th century, we began to understand that there are also other types of light on the electromagnetic spectrum. There are radio waves, microwaves, X-rays, just to name a few. We were now able to study astrophysical phenomena in much greater detail from the comfort of our Earth. And it wasn't until the 21st century where an entirely new type of radiation was observed for the first time, gravitational waves. Together with electromagnetic radiation, this now enables us to study black holes, exotic environments, and the expansion of the universe to give us a more complete picture of the cosmos. Let's explore how we can find something out about black holes using these so-called gravitational waves. But before I do so, let's first look at what a black hole actually is. So black holes are remnants of extremely massive stars that were much more than 8 times the mass of our own sun. And as the star loses its fight with gravity, its core collapses into a black hole. Now, if you imagine our universe like a tablecloth, every object that has mass will create dips in the fabric. In this analogy, the dips in the fabric correspond to the warping in space and time in the theory of general relativity. Time will run slower when you approach one of these dips, according to someone outside of the dip. This is very real, and we rely on this principle to make sure that our GPS system works properly. In fact, clocks on satellites run slightly faster compared to those on Earth. For a black hole, this dip is at an extreme. On the right, you can see that the gravity of a black hole is so strong that even light does not have enough energy to escape. This boundary, indicated by the red arrow, is called the event horizon. Okay, so are these even real? The answer is yes, and the evidence has been overwhelming in the support for their existence. And I will show just a few examples here. On the left, you see that there is a zoomed in animation on the center of our own galaxy, the Milky Way. The dots moving around are stars. And then something is lurking in the center of our Milky Way that is both dark and extremely massive. Massive enough to speed up these stars to fractions of the speed of light. This was one of the best pieces of evidence for a supermassive black hole in the center of our galaxy. This is so groundbreaking that this work received the Nobel Prize in Physics just this past month. On the right, you see the first ever image of a black hole in the heart of a massive galaxy called M87. And this was produced by the Event Horizon Telescope in 2019. You probably recognize this image since it broke internet records on the day it was released to the public. But the existence of black holes has also been substantiated by the detection of gravitational waves in the past 5 years. This is what I and many others around the world have been working on. So what are gravitational waves? By the analogy I introduced before when describing black holes, you can imagine gravitational waves as ripples in the fabric of space-time. And on the right, you can see an animation of two black holes dancing around each other, releasing these gravitational waves as they spiral in. They were first predicted by Albert Einstein in 1916, and it took almost 100 years until they were finally detected by LIGO, or the Laser Interferometer Gravitational-Wave Observatory. It's quite a mouthful. And that was done in 2015, so it's very recent, from a pair of merging black holes. And this discovery received the Nobel Prize in Physics in 2017, which was given to Rainier Weiss, Barry Barish, and Kip Thorne. So how in the world can you detect gravitational waves? Well, you need a gravitational wave telescope, of course. And there are two such detectors in the United States and one in Italy. Here is LIGO Hanford in Washington State, LIGO Livingston in Louisiana, and Virgo in Italy. These make up the LIGO-Virgo collaboration. The three telescopes are needed to properly triangulate where the gravitational waves came from. So where in the sky did these waves come from? I briefly want to talk about how this amazing piece of engineering works. And it truly is amazing. Each telescope is an interferometer. In other words, it detects small changes in the lengths of the 2-kilometer long arms that it has when a gravitational wave passes through it. So two laser beams are sent down each arm and back to a central point, such that the light completely destructively interferes. In other words, the light waves cancel themselves out. Now, when the gravitational wave passes, the arms change in length, and the laser light now combines constructively, causing a bright spot to appear. But what's amazing is that the arms only change by 1/1000th the width of a proton. To put this sensitivity into perspective, let's imagine looking out to our nearest star, aside from our sun, of course, called Proxima Centauri. This star is a whopping 4.2 light years, or 40 million kilometers away. With LIGO's sensitivity, you would be able to resolve an object that is the width of a human hair at that distance away from the Earth. Isn't that absolutely incredible? Now, black holes are only one of the ways that stars can leave behind their legacy. There are also neutron stars, and neutron stars are remnants of collapsed massive stars that are not quite massive enough to become black holes. And these exotic objects are held up by crammed neutrons, unlike our sun. Here is how a neutron star compares to our sun, Proxima Centauri on the left, our Earth, and then a white dwarf called Sirius B. And if you zoom in on Sirius B, that little blue star, then you see near its surface a blue little dot here. That is the size of a neutron star. But keep in mind that neutron stars, although they are so small, that they are much smaller than our planet, they are more massive than our sun. And what does it mean when you have a lot of mass squeezed into a very small point? That means that it is extremely dense. In fact, they are so dense that if you were to get 1 teaspoon of this neutron star stuff, That teaspoon would weigh as much as not one elephant, but 2 million elephants. Now, we talked about black holes merging, where you do not expect to detect anything other than gravitational waves. However, what if you got these dense neutron stars and you're able to merge them together? Well, it happens to be the case that it has been predicted that merging neutron stars can not only create detectable gravitational waves, but also light. And these are in fact nature's particle accelerators. These collisions help us study physics that are not possible here on Earth. And observing one of these would allow for the first ever detection of gravitational waves and light from the same event. So in the animation here, you can see the two neutron stars spiraling in, releasing gravitational waves until, bam, they collide together, releasing a ton of energy, outshining every single star in the galaxy it's in. And interesting here is that you see that this is a visualization. It's an animation. But this animation that you see here is actually describing the real neutron star collision discovered in 2017. It was the first ever discovery of an optical counterpart, so the light, that comes with the gravitational wave signal as well. This is where the talk really gets its name, the lightning and the thunder. Getting both gravitational waves and the light gives you a more complete picture of the astrophysical event. This is like seeing a lightning strike and then using the delay between seeing the light from the bolt and hearing the thunder to estimate how far away it hit. On August 17, 2017, a gravitational wave signal was detected by LIGO and Virgo coming from a neutron star merger. And you can see one of the interferometers here in gray. But astronomers and collaborators with telescopes quickly looked towards the region of the sky that harbored the host galaxy of this collision. So again, these detectors, when they detected the gravitational wave signal, they were essentially able to map out where did the signal come from. Not precisely, but at least where you can look. So the telescopes were used to look at these patches in the sky that are most likely to contain this source. And in fact, it was found in the host galaxy, NGC 4993. Here is a before and after image of the galaxy in which this collision occurred. You can see the tick marks on the right showing the actual explosion, or a kilonova, which occurred 100 million light years away. That means that the light coming from that explosion is 100 million years old. I had the opportunity of a lifetime to participate in this discovery with the Las Cumbres Observatory when I was an undergrad at UC Santa Barbara. This discovery helped confirm several outstanding predictions, such as the production of the heavy elements like gold, platinum from neutron star collisions. So next time, if you have some golden piece of jewelry, just know that it was likely made in a neutron star collision. But also it has challenged 50-year-old astrophysical models, opening up new questions as to how these events actually transpire. One of the most exciting applications of capturing such events is to measure how fast our universe is expanding. One of the most outstanding problems in cosmology is reconciling two types of measurements in our universe's expansion. One of these measurements came from using exploding stars, supernovae. Very specifically, if you know different types of supernovae, these are the type 1As, the ones that involve the white dwarfs that I was talking about. Very, very dim, but very hot stars. And this gave you the local, more late time universe measurements. On the other hand, there's a second type of measurement that was made of the universe. That was using the echo of the Big Bang, using the echo of the birth of the observable universe. And that gave the distant and early time universe measurements. So I do mention that there's two methods. But what's so important about this? Where is the issue? Well, there in fact is a problem between these two measurements. There is a significant disagreement, a gap between the results, where the latter, the second one, predicts a slower expansion of the universe than the first. Now, a possible solution would be to use a completely independent method, free of any calibration issues that may be present in the other two. We now have this independent method. We can use gravitational waves to measure the expansion of the universe to hopefully reconcile this discrepancy. And for the past year, I've been working with Alex Filipenko on this exact problem with promising results. As more gravitational waves are detected in the future, we can test and improve our model, ultimately favoring either the late universe measurements or the early universe measurements. Perhaps none of them will be consistent, and we may have to reevaluate our knowledge of cosmology altogether. The new era of astronomy will surely be full of lightning and thunder. Thank you. I will now leave it up to a Q&A. So if you have any questions, please open in the Q&A chat. You should be able to ask questions. All right. And then a huge thank you to my advisor who cannot be here today, but Alex Filipenko of UC Berkeley for his support in my road to a PhD. And all the funding was made possible for my undergrad research at SURF, and my graduate financial support was given by the Stephen Nelson Fellowship. And of course, thank you, a big round of applause to all the Bay Area Science Festival staff that helped organize this event. All right, so let me go to the Q&A. All right, so I will pick some questions that I think I can answer pretty quickly right off the bat. So one of the questions by Matthew is asking, how fast do gravitational waves travel, or do we even know? So actually, great question. So when I mentioned the kind of predictions that the neutron star detection actually answered or confirmed it or denied, that actually wasn't just the finding that gold comes from neutron stars, but also that the difference between the detection of the gravitational waves from the neutron stars colliding, and the light that we saw, the time in between that was so small that we can pretty much say that gravitational waves travel at the speed of light. And this comes directly from Einstein's equations as well. So that prediction, it's solid. And this is one of those canonical confirmations that in fact, gravitational waves do travel at c, the speed of light. Okay, so let me see. So we have some great questions here. So in gravitational wave detectors, do the gravitational waves cause the motion of the mirrors? If so, does it make our Earth move slightly? So yes, so gravitational waves are they're tricky to understand. In fact, if you prod me more on exactly what it means to be fabric of space-time, this will be a much longer talk. But essentially, yes, the coordinates, as in the positions on the Earth, stay the same, but the only thing that happens is the space between 2 points becomes closer together or farther apart. So the Earth does undulate with the gravitational wave, but very slightly. And now you're saying, okay, so you're telling me if there's an object at point A, an object at point B, and you're saying that their coordinates don't move at all, but somehow they get farther apart? How is that possible? Well, that is because the actual space between the points expands. And this is a pretty difficult concept to get your head around, but this is how you would describe it. So basically it takes light a longer path to get from point A to point B. Okay. So we've got a question about what is a white dwarf? So a white dwarf is a remnant from a star. So our sun actually in its final stages will puff up, it will be puffing up, get larger in size, not necessarily gaining more mass. In fact, it won't be. It'll be getting larger and larger as it evolves over time. And it will have a very light envelope of hydrogen. And because it will be puffed up so much, the sun can't hold on too much to that gas. It easily is blown away. And when your outer layer of the star is blown away, you're left with the core. And this core is extremely hot, but it is also very small. So it's very dim because it's small, but it's still extremely hot. So how do you deal with earthquakes at LIGO? I like this question. So LIGO is so this is a serious concern that they had. In fact, earthquakes are not the only thing you have to be worried about. This is a story that I heard from one of the LIGO speakers before. So they were doing a test run with these detectors, and someone was shoveling snow miles away in Washington somewhere. It was during the snow season, and the way they were shoveling the snow happened to match something that kind of looks like a signal, and they were able to pick up someone shoveling snow miles and miles away with these detectors. But luckily there's three, and the way that they know that something is truly real, like coming from a neutron star, is they have special models. They look at a signal and they say, okay, is there anything artificial that can make this signal? And they kind of have a probabilistic argument, more or less likely. So if it's someone shoveling snow, be like, yeah, this kind of looks like it, but the Hanford detector, the one that's in Washington, got this shoveling snow sound basically, but someone in the detector in Louisiana didn't, and the detector in Italy didn't. So that's another way they can say, okay, so it only happened in one. That's probably not. It's not. It's an artificial signal. Didn't come from out there. Okay. See. So is so I'm seeing another question here that's saying, let me scroll back up. Okay. Is there an object more massive than a neutron star but less massive than a black hole? Um, this is actually a good point here. That one of the problems we're actually working on as well is to figure out how massive does an object have to be in order for it to be a black hole or a neutron star. There's actually one of the big problems right now is that we don't, there's this gap. We only see neutron stars no greater than maybe 2.5 times the mass of our sun. And we don't see any black holes that are less than 5 times the mass of our sun. So where's the in between? Is there anything there? So we actually are looking for very massive neutron stars. And the most massive one ever found was actually done with LIGO. It was a neutron star black hole merger. I wrote a paper about this, and the neutron star there, quote unquote, we still don't know because it is so massive. It could easily be a black hole. But you do have this question of what constitutes a neutron star versus black hole. And we still don't know the answer to that. But yes, black holes can be up to 10 million solar masses, not just 1 or 2 times more than solar masses. So those are the supermassive black holes, the one you would find in the center of our Milky Way. All right, so let me see here. And do upvote any questions that you see here that you want answered as well. So is a black hole an actual hole, or is it matter that is extremely dense? This is a great question. So Einstein would probably, well, actually more like Schwarzschild, one of Einstein's predecessors, they worked together on the whole theory of general relativity back and forth. There are people who would argue saying that you shouldn't think about it as matter being packed into one spot, but more of the curvature of space itself is dictating how much matter something has. So this is a very difficult concept to answer. However, I can say that anything that goes into a black hole, it'll be ripped apart into something that does not resemble matter at all. It'll be torn apart to its most fundamental particles. All right, any other questions that I hear? Okay, so okay, let's see. So we've got, so someone asked quickly about like how dense the neutron star is. So again, it is so dense that um, you could fit basically the mass of the sun, or up to 2 times the mass of our sun, into a city like Berkeley. That's how much matter is packed into a small point. Um, and the kind of force is the kind of things that happen near the surface of these stars is astonishing. If you were to try to stand on the surface of one of these, you'd be ripped apart and spread across the star in a thin layer. That's how intense the gravity is. The magnetic fields are also incredibly strong. You definitely do not want to be near one of these. So someone's asking, if that the Earth was sucked into a black hole, we wouldn't feel anything, but we would be ripped apart externally. All right, so this has 2 points here, two little nuanced questions here. So the first one is really asking the free fall question. If you were jumping out of a plane and you didn't feel the air against your skin, for you it would look like you're free floating. You're floating and nothing's happening to you, but in fact you're barreling down towards the Earth. So you can imagine yourself in an elevator that's cord is snapped. So hopefully that never happens. But if the cord snaps, you'll be falling with the elevator. Everything would be weightless. You wouldn't actually be able to tell that you're being pulled into something. And as for being ripped apart, this is actually relating to the spaghettification that happens if you get near a black hole. So this is a real term used in astronomy, seriously. Spaghettification occurs when you get so close to a black hole that the pull, the tug of the black hole, the gravity, so the gravity of the black hole is so strong at your feet compared to your head that it ends up pulling at different forces. In fact, it can pull so hard that it can just literally rip apart the atoms that are holding you together. That's how intense this pull is. What's a really cool argument is that if the scariest black holes are actually the supermassive ones, because it's not the force at which they pull that's scary, it's the difference in the forces. So the force that you feel at your toe and your head for a very massive black hole, because they tend to be larger, the difference from your foot to your head is smaller for when you have a black hole that is massive compared to a less massive but much more compact black hole where your head and your toes are a significant fraction of the size of the black hole, and that ends up pulling at your feet and your head much more. So spaghettification will happen more so for the smaller mass black holes. So don't be fooled. The smaller mass black holes are in fact more dangerous than the supermassive black holes to be near. All right. So you can detect black holes multiple ways, again, with gravitational waves. So that's actually these ripples in the fabric of space-time that I was talking about. However, you can also see not the black hole itself, but the shadow of a black hole. So if there is something near a black hole that it wants to eat, that stuff will fall in, and because it's falling in and it's parts of it are hitting into each other, it creates a lot of heat and it starts to glow. So sometimes you get this ring around a black hole that you see here in one of the evidence for black holes that I have here. I'm going to scroll back up. Let's see, where is it? Here we go. On the right-hand side, M83. So no, that's an actual image of a black hole, but the black hole is that shadow part inside. The glow around it is material that's being spun around so quickly that it's glowing from how hot it is. And there are other various ways as well. So it's not necessarily bad that the universe is expanding, it's that we don't know how fast exactly it's expanding. In fact, the universe is not just expanding, but it's accelerating in its expansion, which is something I didn't talk about at all today. So these are the exciting things that cosmology has been bringing forth. And in the past 5 years, the Nobel Prize in Physics, for 4 out of 5 of those was given to astronomy. So it's really the golden age of astronomy right now for cosmology. All right, since it is 5:59, I think we have to call it at this point, but thank you everybody for coming, and thank you for the organizers for hosting the event. All right.